Hello, my name is MHarmon. I am a student in ADTA5550, Deep Learning with Big Data. Today I will be presenting the findings from my final project. In this project, I explored the architecture of a convolutional neural network in the classifying of color images. I would like to begin this presentation with an executive summary. The convolutional neural networks are networks optimized to model images and other types of multidimensional data. The final project implements and then assesses the performance of a CNN network as trained on the CIFAR-10 image data set. Image data, including photos, handwriting, artworks, or any other data that can be represented in a multidimensional grid-like vector of numbers, can be processed by CNN networks. Convolutional neural networks are a specialized type of neural network for processing data that has a known grid-like form, including images and time series data. A CNN network trained to classify images is evaluated by assessing the accuracy of those classifications. What is the proportion of images that were correctly classified? We will begin the discussion with a discussion of image data. What is image data? Image data is any data that can be represented as a grid. When speaking of images, it's a grid of pixels. It would include handwritten text, scanned documents, photographs, maps, even video and audio materials, as these too can be represented in a grid-like pattern. You'll notice I've included two images on this slide. One is of a leaf from a diseased plant. You'll notice the spots on the leaf. And one is a handwritten representation of the number 9. You'll see that it already has been measured out for a number of pixels. It's a grid 28 by 28 pixels in shape. This next slide is relatively complicated. It's a description of the properties of image data. As I said, image data we receive has been a collection of pixels. Each image has been in a grid form, either 28 by 28 pixels in shape or 32 by 32. As you can see, a 32 by 32 pixel image would have 1024 pixels. They grow quickly. Each pixel is a number in the range from 0 to 255. 000 is black, 255 is white. A color image would have 3 dimensions: width, height, and depth. The width and the height are considered the 2D size of the image. The depth is the layer of color. This is represented in a color photograph in red, green, and blue RGB values with a depth equal to 3. Grayscale has a depth equal to 1 and represents shades of black from white to black. I've included a satellite photo which demonstrates that this can be rendered into a grid of elements, pixels, representing the brightness of each pixel with a numeric value. This grid can be processed by a computer and displayed. The initial request for this project was to search the internet for data sets consisting of images. One of the data sets I found after searching through the internet was a collection of different category of leaf images. This data set had 4,500 images. It's broken out for 12 plant species. There's 2 types of leaf within these species, healthy versus unhealthy. This data is available under an open access licensure and is available to all. The difficulty and challenge of this data is it's only 4,500 images. So the researchers who put this data together recommend that this data be augmented when used to train or used in classifying leaf data. In the prior slide, we discussed data I discovered after an internet search. This project, however, focused on the CIFAR-10 image data. This is 60,000 images of common everyday objects. These objects are categorized into the 10 categories you see listed next to the grid of sample images. airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. There are 5 sub-data sets of 10,000 images apiece. The images selected for these subsets are randomly selected. As a result, they may not be equally proportioned among all the categories of the data. Each of these images is a set of pixels 32 by 32. There's 6,000 images per class, and the critical aspect of this data versus other data we might have seen in the class is that these are color images, color photos. This data has been made available to us. It's a large data set. It was downloaded as per the instructions we received from the professor, and this is the data on which my CNN neural networks were trained. I would like to begin the next section with a general discussion of convolutional neural networks. These networks are a class of artificial neural networks that are optimized to learn from image data. They are derived from feed-forward neural networks. In a feed-forward neural network, the flow of the processing is from the inputs to the neurons in each layer and finally to the output. The output is a function of the inputs of weights and biases assigned to the inputs. I will move to the next slide. Thank you. What is a convolutional neural network? These are networks that are optimized for processing image data. The models learn to classify directly from images. They are particularly good at finding patterns in the images, including the ability to recognize objects, such as objects, faces, and scenes. These networks learn directly from the data, and they eliminate the need for manual feature extraction. What makes these neural networks so powerful in terms of image processing versus a traditional neural network? It's the number of weights that would be required. Even in a very small, simple image of 32 by 32 times 3 in shape would require 3,072 weights. Fully connected structures do not typically scale to larger images. Multiple neurons for each pixel would multiply the parameters of a traditional neural network very rapidly. And these types of networks avoid the overfitting due to the expansion of the parameters that would occur in a more traditional neural network. In this next slide, I'll be discussing the CNN network architecture. There's 2 major activities within this architecture: feature learning and classification. This architecture is essentially a combination of 2 subnetworks. The first subnetwork is the feature learning subnetwork, and this is the convolutional aspect of the network. It includes the convolutional operations, the activation function, as well as pooling of the data, which essentially is data reduction, and I'll discuss that a little bit more in detail as this slide presentation continues. The second component is the fully connected network, and the fully connected subnetwork is very similar to a normal multi-layer neural network, a multi-layer perceptron network. It comprises the fully connected layer. This layer processes the outputs from the feature learning subnetwork and essentially finishes the output of the ultimate output of the network and sends it to the next step. The core idea on this slide is convolution. This is the core idea behind convolutional neural networks. Essentially what this means is the merging of 2 sets of information, 2 functions. This is described as the convolutional operation. This operation is performed by sliding a filter over the input. At every location, matrix multiplication on the elements of the matrices and the results are summed. This sum goes into a feature map. Stride is the amount that the filter moves or walks through the input during each iteration. I've included 2 figures, primarily blue larger figure that's 5 by 5 with a small green subset within it of 3 by 3. This is the input with the filter for the data. The second image is the filter map, the result of the processing of the input by the filter. The convolution filter, the kernel, is green in this image. It's a 3x3 convolution filter, and this convolution is called a 3x3 convolution due to the shape of the filter. The feature map is also constrained by the shape of the filter. Within this data, in real world, this is a two-dimensional piece of data, but within the real world in an image data, what we would see is an image represented by a 3D matrix with dimensions of height, width, and depth. A color image would show 3 color channels, red, blue, and green. A black and white image would only have 1 channel. Multiple convolutions are performed on an input. Each uses a different filter and results in a distinct feature map. Ultimately, these feature maps will be stacked to create the final input of the convolutional layer. The next layer I'll discuss in the feature learning subnetwork of the CNN network architecture is the pooling layer. The pooling layer is intended to reduce dimensionality. How this occurs is pooling aggregates the multiple values from a feature map into a smaller data representation. These have invariance to small transformation. It reduces the size of the output from the feature map layer, from the convolutional operations layer, and reduces the amount of data going in as input to the next layer. This allows for faster processing. And theoretically, this keeps the most important information from the image available for the next layer. There's 2 types of pooling, max pooling versus average pooling. Max pooling would take the maximum value in the max pool. In this example, it's a 2x2 window with a stride of 2. If you look at the red corner, the maximum value is 6. That would be the one that would be sent, that would be aggregated into the smaller grid. Pooling reduces feature dimensions as a function of the pooling parameters. This can reduce the amount of data quite significantly. If the input data to the pooling layer is a grid of 32 by 32 by 10 and you use a 2x2 window, the output data from this would actually have a 16 by 16 by 10 grid structure. The height and width would be halved, but the depth is not changed. This would reduce the number of weights by 1/4 for the ultimate input to the next layer. And when dealing with millions of weights, this reduction would be significant. Pooling is typically performed using a 2x2 window with a stride of 2 without padding. In this next slide, I'll be discussing the limitations of the convolutional operation layer. Within this layer, you run the risk of a loss of data detail. What this means is as you iterate through the convolutional operations, as you saw, you go from the input grid shape down to a smaller feature map shape, and even further down into a smaller pooled data representation. As I said, through each of these iterations, the image inputs get smaller as they iterate. Details are lost, and our recognition accuracy can drop. You can run out of latent pixels. The convolutional neural networks, if you have too many layers within the convolutional layer, if the architecture is too deep, you can very quickly essentially run out of data and overfit the model. Padding allows you to avoid some of this. What padding is a method to maintain the dimensionality of the feature map or the input into the into this layer, into the final layers. And what it typically involves is that you pad the data with zeros along the edge. Padding typically is used to preserve the size of the feature map and maintain dimensionality across the layers. On this slide, we'll be discussing the second major subnetwork of the CNN network architecture, the fully connected network. The fully connected layer produces the final output. It acts as a form of filter on the convolutional layer's output. First, the outputs from the convolutional layers would need to be reshaped or flattened into a vector. A final features map with dimensions, for example, of 4 by 4 by 512 would be flattened into an array of 8,192 elements. This flattened vector would be fed into the fully connected layers. These layers would be producing output that would be fed into the final activations functions, the softmax. From there, some of the outputs from this activation function, however, would be dropped before the final outputs were produced. And as I said, the fully connected network is very similar to a normal multi-layer neural network, a multi-layer perceptron, which we discussed earlier in the semester in this class. In this section of the presentation, we will be discussing the CIFAR-10 dataset and discussing on how the CNN network, the convolutional neural network that I implemented and trained on this data, performed when using this data. Learning the CIFAR-10 image data, my implementation of the CNN network. As you can see from the grid of images that I have included on this slide as we previously discussed, this data, these images, are highly variable. The aspects of and perspective of the images change. The lighting and the background show significant differences. The images are taken from a variety of angles and sides of the object, including the front, back, side. Some of them are the bottom, some are the top. You'll notice even some of these images have only partial objects in them. The challenges of modeling this data would include that color adds significant dimensionality to the data, the variability of the images themselves, and quite potentially the loss of details when these images were pre-processed for use in training these networks. As you can see, even just a brief glance at this 100 photos shows that these images are very different. They even have, a lot of noise in the background. They have clouds, extraneous buildings, images, information, noise. The color background may also obscure the edges of the target objects, and this may become important as the model is trained. On this next slide, I'll be discussing the design parameters of the CNN network. These will be the specification around these model characteristics for the CNN neural network that I'm implementing to train on the CIFAR-10 data. This network will contain two convolutional layers. These layers, of course, will consist of the computation or filtering layer and the pooling layer is used to reduce the spatial size of the result. As you can see, the image shape will be a 32 by 32 by 3 image matrix. The filter shape will be 5 by 5. The stride will actually be a 2-step stride, and the convolutional layer, as I said, is 2. The data will be trained using batches of 100 images. The number of batches or steps would be 5,000. Number of images included in the training data set will be 50,000. The number of images on which this data model will be tested will be 10,000 images. And there will be a dropout layer in the fully connected network, or the fully connected layer. On this slide, we'll begin the discussion of the evaluation of the accuracy of the model. After I designed and developed the model and implemented it, trained it on the data, I then proceeded to the testing phase of the model design process. As you can see, I have provided a graph of the accuracy of the data. And accuracy essentially is just the number of correct classifications over the total number of classifications available. So it's a measure of the error rate or the correct classification rate. And if you look at this, this model did a particularly poor job of classifying the CIFAR-10 images. At its peak accuracy, it only accurately classified approximately 64% of the images in the testing data. While this is better than a flip of a coin, which would generally just give you odds of a correct answer about 50% of the time, it is not impressive accuracy. As I reviewed this accuracy, went back and reviewed the data, there are there's any of a series of reasons why this may be true. This may be that the data lost significant amount of detail in the pre-processing. It may have also lost detail during the dimensionality reduction through the iterations through the convolutional layer. The filter kernel may have reduced the data by too much. The pooling may have reduced the data by too much. As a result, this model gave a relatively poor classification results. So I will be considering some of the reasons for this as I proceed through this project. In this next section of the presentation, I'm going to conduct a comparison of the performance of the CNN network using the two distinct data sets that we were exposed to this semester. That would be the MNIST data set and the CIFAR-10 image data set. The MNIST image data set is a data set of image consisting of handwritten numbers. These numbers are between 0 and 9. The training data set contains 60,000 images. The testing set consists of 10,000 images. I've included a screenshot of a small sample of image data here. They're black and white images. The numbers are in white. The background is black. Data has differences in how each of the numbers were written. If you look at the one, you can see that it's kind of a vertical slash or a slash at an angle, or and that angle can be left or right. You'll see that the 2 has a loop at the bottom. So these data, this handwritten, there's a lot of variability in this handwritten data. But you'll notice that the background is black. There is a grayscale, so this is not three-dimensional colored data. You'll also notice that the background does not contain extraneous noise. It's basically just a black background. This next slide is just an overview of the specification parameters for the CNN network. You'll notice that it's the same parameters, same specifications as used and discussed in the prior section of this project against the CIFAR-10 data. There is no significant differences other than the data on which the network was trained. On this next slide, I just want to briefly go over the accuracy of the CNN model that was trained on the MNIST data set. As you can see, over 99% of the test images were correctly classified. This model was very accurate, became very accurate within very few repetition data training steps. I think the explanation for that is that because this were black and white images, the primary dimensionality was the two-dimensional size of the matrix of the data itself, the images themselves. These images had fewer features, were easier to model given that the background was black, and given that it's a white lettering, white handwriting on a black background, the boundaries and edges of the numbers were easier to identify. At this point in the project, we were asked to compare the results of the model's performance on the MNIST data versus the performance on the CIFAR-10 images. As you can see, the modeling the performance on the CIFAR-10 images was significantly inferior to the performance on the MNIST data. Why this might be the case? the images, the data differ fairly dramatically. As I said, the MNIST data was black and white images versus color images in the CFAR 10 data. Single channel versus 3 channels. The MNIST data was a uniform background versus typically a very noisy background for the color images in the CIFAR-10 data. My guess is that means there are far fewer features in the images in the MNIST data, which are easier to model, and this makes the boundaries and edges of those images much easier to identify by the model. After considering the gaps in accuracy of the network as applied to the CIFAR-10 dataset, I have proposed revising the network to see if I can improve the performance against that data. In this section, we'll discuss the results of those revisions to the network. On this slide is a discussion of the revisions to the specifications of the design parameters around the network. After comparing the results with the results of the MNIST, I considered several options. One would be just basically increasing the batch size and the number of steps, and this did not seem, given the curves and how flat the curve ended up being so soon into the training, neither of these options seemed likely to impact the accuracy of the model. As a result, I gave consideration to some of the other aspects of the model that might result in loss of data and loss of the ability to classify and recognize the images. I think the one that I became focused on was the filter shape. I felt that perhaps the filter shape was reducing the data a little bit too much before it entered the pooling layer. So I opted to use a smaller filter, a 3x3 filter with a stride of 2. Mostly I kept the other parameters the same. This next slide summarizes the evaluation of the accuracy of the model after I made my revisions. This model performed poorly on the test data. It classified correctly only about 66.4% of the images presented in the test data. While this is a marginal improvement over the 64% accuracy in the original model, it is not a substantial improvement. It's only about a 3% improvement over the original model. My expectation, I guess, was that using a tighter filtering window would have increased the granularity of the data, would have increased the data available to the next layer. That does not appear to have helped in terms of improving the accuracy of this model. Again, the reasons why this model may perform so poorly is that there may be data lost or data details lost in the pre-processing as these very complicated images were reduced to a smaller grid of pixels. There may be data loss due to dimensionality reduction during the convolutional layer processing. The filter kernel may still be reducing the data by too much. And frankly, the pooling may also result in less data and a failure in the recognition and accuracy of the model. This is the last model I'll run on this. And that would end the project. In conclusion, I have to say that designing a network involves both art and science, and image data presents unique challenges in deep learning. Clearly, not all image data is the same. Black and white images may have less features and be more easily modeled than color images. The complexity of images may include a lot of noise that may make this type of data much harder to model generally. And as this demonstrates, a model that works almost optimally for one type of image data may be nearly ineffectual against different image data. I think the biggest issue may be excessive background noise degrading the effectiveness of a model. I think as I go forward, and studying neural networks. It would be interesting to see if a more complicated model might have better modeled and been more accurate when used against the CIFAR data. That may be the next step in my progress through the learning about neural networks. I want to thank you for your time and the effort you took to listen to my slide presentation, and good luck in the future. Thanks.